I'm the other co-founder of Ponte Communications. We do automated network device management, essentially network configuration and firmware management software, and we're going to talk about the actual issues that you run into in trying to drive devices in an automated way. So, at the risk of stealing the quote, Epstein's rule of large numbers, I'm sure you're all familiar with, responsibility for large numbers of anything that must be individually managed is a real pain. He actually toned that down. The original language was a lot worse. If you run a large enterprise or a large network, then what you're looking at all the time are a lot of individual things you need to go touch. It's really time-consuming. It's really irritating. And it gives you a lot of chances for people to fumble finger. Gives you a lot of chances to find out that the real environment in the world doesn't resemble what you thought it was. And in fact, a lot of your operational time is spent going and determining what am I actually looking at on the ground. What we've been told, talking with all the providers and all the enterprises we deal with, are that they have a lot of different things, whether that's different constituencies who are looking for different services from them, whether that's different pieces of equipment, including the 3 from the 5 different vendors who've gone out of business over the last decade, who they have a whole lot of, but they're still supporting. Dealing with a lot of the different staffing issues the previous panel talked about, and also being exposed to a lot of attack. We care a lot about security, so we spend a lot of our time looking at the security implications of operational models a lot more than many might. The other 2 additional challenges that are sort of orthogonal to just the environment of running a large network are high employee turnover and the fact that you've got a lot more folks in there than you have folks who really understand the equipment they're working on all the time. So you've got to be able to deal with a lot of good communication, try to help good communication inside the organization. Let's take a look at the normal sort of network you're looking at. This may be a familiar sort of picture. You've got your core WAN, somewhere the rest of the internet is coming off of it through a set of peering points. And then regional POPs and observation NOCs, control NOCs. And customers are eventually strung out on the other side of those POPs. If we drill into that a little bit, we see that while conceptually we think of there being a single router between the core WAN and a regional POP, there's actually a lot of equipment tied up there. You start out with your core routers. In virtually every sensible case, those will be heavily parallelized. You've got additional switch fabric sitting there for load balancing and to provide additional services inside your NOC, perhaps you're providing some additional layer 2 services. And then you've got access routers. When we say access routers, we're thinking things you plug a lot of cards and really big cables from the telco into. And somewhere way out there are customers. And so when your diagnostic process and your configuration process are looking at all of these devices, possibly including ones all the way out of customer CRAN, and trying to orchestrate that. This screams for automation. We have an automation system. The points I want to show you here are specifically, we use plug-in logic to do device manipulation. In the public space, you see something very similar, although orthogonally implemented with Rancid. The tools have been around for a long time. Everybody knows about Tickle Expect, except for some unfortunate circumstances. I actually found some people who were doing manual Perl device management recently. They were very frightening. And the rest of these slides are going to be about how you actually make Tickle Expect work for you to control devices well. Where are the gotchas? So there are a handful of basic problems you're trying to fight with. In your sort of idealized world, you can say, well, what do I do when I change a device, when I update a configuration? I log into it, it gives me a password challenge, I type some stuff at it, maybe I tell it to copy a config file because I don't really believe in configuring things dynamically if I can avoid it, and hopefully I keep a good trail somewhere. When you try to automate this, you suddenly find it's a lot more complicated because there are a lot of bad events that you as a human are just dealing with gracefully that now you have to teach this poor little chunk of Tickle and expect to deal with. The most serious of those that we've seen are the ones listed here. Buffer skew and device prompts, timing and reset behavior, terminal servers and other exciting things that can happen between your control channel and your control source and your device, dealing with firmware, mostly in the context of I'd really like to automate managing firmware too. High availability, other bad things that can happen to your control channel, and then dealing with existing configurations, because everybody's got a network running now. If you're starting to automate, you want to start with the information already on the ground. Prompts. People use all sorts of prompts. Many of them are evil. Your sort of naive expect code again says, well, if I see a pound sign at the beginning of the line, then that's probably a prompt. The problem is that the definition of beginning of a line is pretty squishy. Often you'll see things like somebody says, authorized users only, and has lots of pound signs in it because that's a good clue for humans. You may have differing custom prompts to indicate what state the device is in. You may even want to put in custom prompts. I've seen a lot of organizations try to embed location information into the prompt as an extra hook to make sure that when you're talking to a device, it's actually the one you intended to. Many of us have been on the wrong end of the, you mean that wasn't the router in this customer's site anymore? And it's not fun. So your logic has to be able to deal with the custom prompts. That means you either need to know what the prompts are and very rigidly control them, which works great until you get somebody else's network connected to yours. Or you need the logic to be very flexible. So the strategies we recommend, first, that you resync early and often with unique text you're generating, and potentially that you're using time tracking as an additional sync. So here's an example of synchronizing the buffer, forcing there to be known text in the buffer coming back. Most devices, unfortunately, don't let you say echo. So it's not like with a shell you can say echo some string I'm looking for. So what we've done in the example here is we've actually forced a known response from the device. It's just interstitial text. We're sending a request for a usage command. We know what the usage command looks like. We get it back. We back up and say, okay, I know that I have now forced the prompt. And by the way, if anything times out here, I need to scream bloody murder and get some help. Moving on to speed and timing, devices often have bad reset behavior. What I mean by bad in this context is not trivially predictable. If resets take 3.5 minutes per device, if resets take 3 minutes per card, well, that's really bad, and it's in control when I do it. But the real problem is when a reset could take anywhere from 20 seconds to 3 minutes, and I don't know before the fact. You also may find that devices don't disconnect when you think they would. This is particularly horrific on large Cisco routers, unfortunately. When you tell them to do a reload of a large config, they start doing the reload work. But they'll still accept incoming connections, because after all, you should route packets for as long as you can. And that's pretty good, except for the fact that it also means accept control connections while it's busy doing all of its homework and housekeeping to restart. So that means if your logic just says, I'll go clipping along, I'll issue a reload because now I want to restart the machine with my new shiny configuration, and then I'll reconnect, it hasn't finished shutting down yet. It's still running into the old config, which will wisely give you the same saved config it was mere moments before. And you'll say, oh, okay, I'm cool, I'm cruising along in my control session, and then you'll get a disconnect from space. So your logic needs to look around to find out what state are you actually in. The other related timing thing is that many devices don't deal well with getting data faster than they want it. I don't know why a lot of router hardware that deals very well with very, very high-speed connections gets really cranky if you start pumping data to its control channel at 44 kb, but I've seen it happen a lot. Now, to some degree, you can slow that naturally. Again, you've got a lot of prompt syncing going on, hopefully, and that's going to slow things down a little. But that's not enough, particularly if you've got intermediate devices, whether that's terminal servers, which we're going to talk a bit more about in a second, or whether that's interesting tunneling between you and the control channel. So drilling into speed, the first and foremost thing that you need to do is really just put in good sleep conditions. Put in weights where they make sense. Actually take a look at devices, understand what that class of device wants. I know that seems like optimizing away from the general case, but it really is what you need to do. You actually need to go look at what your actual devices do, code that back into your script. You'll need to make a few decisions. You need to put some logic in there to understand, am I dealing with a 2500? Am I dealing with a 7500? Am I dealing with the newest, fastest thing from Juniper? But your set of decisions are pretty small, and it's really easy to trap yourself into, well, I'll do something really clever, and find that your clever logic is harder and harder to maintain, particularly as you go from one device family to another. You'd really like for that chunk of code you wrote 2 years ago to drive 7500s to be pretty easy to turn around and drive Junipers today, or to drive weird connectivity boxes. Again, you really do need to take advantage of the expect commands to control typing speed. This is one of the really cool things. The expect book talks about it a bit, the O'Reilly expect book, about dealing with slowing command speed. Because a lot of particularly older communication devices get very, very unhappy, and you lose state completely. Unfortunately, it's device-specific whether lose state means it stops accepting commands and issues you an infinite number of control Gs, or remembers the last 40 characters you typed and does something basically random. Terminal servers. Terminal servers are exciting. Lots of people set up these beautiful little pop structures with terminal servers running to all of the devices that they've got remote control of power and console. It's a really good strategy. It means that you can go and unwedge a device in a lot of cases that otherwise you'd be putting somebody on a bus, having them drive a truck out. That's expensive, it's time-consuming. There's a lot of, I feel what's really wrong while we're getting there. The downside of that, if you're doing automation around it, is that you don't know who the last guy who touched the terminal server was. You don't know what state they left the device in. You know what your runbook tells them to do, but in fact, maybe they left it in the enable mode. Maybe they got to, I'm logged in, I'm about to enable it, I got to walk away and find out there's one other piece of data, and then they got hit by another interrupt. So your logic needs to deal with, I don't really necessarily know what state I'm connecting to. And it also has to deal with the fact that terminal servers themselves are known to do kind of random things on occasion. Notably, if you need to reset the terminal server, it may helpfully take every device connected to it with it. So we've got some discussion in here, some examples of how do we deal with that. So first, we go looking for what state the device is in based on the prompt we get back as soon as we connect. And that's both a matter of synchronizing into the mode we expect it to be in and dealing with local security policy. Some organizations figure, hey, we set up these terminal servers, they're so our operations organization can get at them. The connections themselves are very well controlled, maybe off to a secure TACAX plus server or something like that. Deal with whatever state you find it in. Look around as part of your state acquisition. Other organizations say if you ever connect to the terminal server and you find the device has been left in enable mode, try to track down on paper who was in it last and go beat them up about it. And if you find out that they didn't leave it, you've got a security event. And so, again, your automation logic needs to make sure that it's leaving the device in a state that's expected and that it's triggering the same way your organization would if it finds the device in a state it didn't expect. So we go and do the normal sort of login thing, doing a parameterized login to deal with maybe we're living in a TACAX world, maybe we're living in a world where you get no password challenge at all. Maybe you're living in a world where you're connecting to a 1900 where you have to throw it from menu mode into command mode. And once we get it into basically the access state we expect, then we try to start talking to it. And there's a little bit of logic in here, if I can get to some of you at least we'll look at later, to deal with things like, what if there's no password? What if there's a password and I didn't expect one? Most of those are conditions where you really want to not only have your logic catch it and error out properly, but you also want to alarm off to your operator organization properly. The other fun thing about terminal servers is that they're often the device's notion of the true console. So the device will be cheerfully sending output to them whether you want it to or not. Helpful things like, my line has just gone up and down. Well, that's what it should be doing since I'm configuring a new line, a new interface setting. And what this means is that your scripts are going to be getting, from their point of view, spurious messages interspersed through a real output that they actually want. You may also have pagination, that the device is desperately certain that every terminal in the world is 24 lines and it's going to give you a more prompt whether you want it or not. So what do you do about that? The first thing you do is you try to suppress the output that you don't expect. If you can narrow down what the device is going to say back to you, then your logic becomes a lot simpler. You end up having nice expect blocks that say, I expected a username challenge, I'm going to give it one, rather than having blocks that say, I expect a username challenge, but maybe I'm in a weird mode, much like the one you saw a couple slides ago. So you try to turn off everything that might be randomly being thrown at you. But fundamentally, the device is going to do what the device wants to do. Some product manager somewhere found out that the one organization he was building this product for always used 30-line terminals, and you can't turn off more. So at that point, you need to actually do some interpretation of the data to make sure that it looks like what you expect. And the general rule you're following here, good old-fashioned networking rule, be liberal in what you accept and conservative in what you send. Match the spec as closely as possible, but understand that someone somewhere will decide that it's really important for a device to report in human-readable terms instead of nice, consistently formatted machine-readable terms. Firmware. Some organizations we've talked to have really got a pretty good handle on firmware management. They've got some automated scripts that do basic updates of all the equipment that they've got a lot of, and they keep good records. They put everything on TFTP servers and make sure that those are accessible. Other organizations have tried a couple of times in a row and decided it's just too hard. And you've got two sort of sets of concerns. One are configuration file issues. What do I do if my underlying command language changed between two different versions I'm dealing with? That may mean commands have been added or removed. That may mean that there are semantic differences. That may mean that you need to do a wholesale change, like going from CatOS to iOS. Ideally, your structure will be able to deal with that kind of process where you're going to need to connect, possibly load a new config, perform an update, possibly now load a new config because the world may have changed. There's some structure in here. The other set of concerns, and these are purely operational, are transfer concerns. First and foremost, distance is not your friend. The farther away a device that you're trying to manage is from the point that it's being managed, whether that's the TFTP server, the console station you're telnetting to from the NOC, the more exciting things can happen that are unfortunate while you're trying to manage it. In your normal config session, this isn't a big deal because they're short and have small volumes of data. In a firmware update session where you can have many megabytes potentially, this can become a real problem. On the system side, we solve this by doing staging and actually using bigger hosts with bigger disks because of that. On the device side, you need to deal with it by putting TFTP servers closer, by putting some other sort of control infrastructure really close to the device. You're also trying to deal with pilot error. This is part of the biggest reason that you want to automate something like firmware updates. You want to remove the possibility of accidentally giving the wrong image to the device and of accidentally giving a valid file that just doesn't happen even to be an image at all. These are both things that happen in real operations. They're very frightening. Again, they involve someone has to go and physically manipulate the device to bring it back to life, generally. Next couple of slides are about failover. Most things in your operation that you care about, you've got more than one of, and they're in parallel. And that's going to range from devices that don't have any innate sense of parallelism to devices that are very strongly coupled. So looking into the PICs, sort of our perfect example of something that's strongly coupled, your first and foremost automation problem is they have a notion of which one's active and which one's standby, and of which one is the primary and which one's secondary, and it may not match yours. Because, of course, your script has been written assuming I'm in a normal sort of world. And the device, when you're connecting to it, it may still be in the failover that it cut into 3 months ago when one of your lines went out. So you need to code defensively. Similarly, if you're going through terminal servers, you may find that devices don't really match the identity that you thought they did because they've since swapped. You can also encounter change volume limits, which I'm going to go into more on the next slide. And you can encounter new config commands that are specific. So this is an example of some code that is actually trying to go scope out what's happening on a failover device when it connects to it. So, it connects in, it says show failover, and now you see a lot of timeout logic in here, trying to deal with all of the ways the device can choose to not come back in a good way. Maybe it didn't actually get the connection, maybe it didn't actually get the cable status back. Hopefully at some point, though, you get an actual set of strings that say this is what the device is currently configured to do. And at this point, you actually need to go interpret that to set your script's expectations about who's the secondary, who's the master, who am I talking to right now. And here we see an example of some code that actually goes through that process setting. Again, this is an opportunity to cry for help if what you find on the ground is too far away from what your logic is prepared to deal with or what your organization has designated as the operating policy. So once you're finally actually starting to talk to the device, you get the next set of constraints. And this is a real issue with tightly coupled failover. We found in the PIX case that many versions of PIX, if you give it more than about 200 commands on a configuration session with a failover device, as soon as you try to write that, it just goes away because the primary and secondary devices are talking to each other and they've blown a stack buffer somewhere important. So your logic needs to expect and deal with well-known limitations of the device like that. What we show here is an example of actually ratcheting down how many lines we send out and making sure that we're always sending right configuration commands at the right time. Control channel problems. Bad things that happen between you and the device. The most common that people code around is loss of connection. Yeah, I get a temporary disconnect. That happens all the time when I'm logged in. No big deal. And they write a lot of expect that sort of naively assumes that those are retriable states. This is often a bad idea because a lot of your configuration commands will leave the device in a state where if you just start typing commands to it again, it will now fail in very weird and hard to understand ways. So what we found instead is that you need to actually be pretty clever about, did you get an EOF at a time that causes you to not restart your session? Or did you get an EOF at a time where you know basically what's going on and you're prepared to go back in? If you get an EOF right after you log in, well, that's only suspicious if you get 3 of them in a row, at which point you say, there's something really wrong here. But if you get an EOF in the middle of setting up a bunch of line statements, maybe I stomped on myself. The other big idea that we found is you want to distribute control. You want to put the actual point where control is coming from as close to the device as possible. Again, that really ratchets down your risk of exposure to the connection failing. It also makes the session vastly more secure. We've had various carriers who own their entire layer 2 say, oh no, I just assume my wide area network is secure. I don't worry about it much. I just run bare telnet over it. This is horrifying. Anyone who knows the statistic on what fraction of security threats are from inside your organization. And by inside, we don't mean your operators are attacking you. We mean randoms over in accounting get it into their head that they should be able to go find out what's happening in your operational network. It's useful. So the final couple of slides I wanted to talk about are about interpreting found configurations into data and using what's already out there in the network. So we've actually done a bunch of logic, which was far too voluminous to put on this slide deck, unfortunately, to actually go and pull information out of the PICs. I'm just using the PICs because it was a straightforward thing sitting in front of us. Where we actually go out and pull out, all of the simple stuff. You can parse in interface names, security levels, and most of your interface settings out of found configurations pretty easily. You can parse out the encrypted enable and access passwords. Although hopefully you're running with enough encryption that you can't parse out the original passwords. So in an automated system, you want to be able to expose the found configurations, retrieve them back, because of course part of your goal here is to look at what's changing over time, and store that away, and then being able to extract some metadata out of that for reports, perhaps for a database control system. It's really worthwhile. It also serves template-based configuration generation where you've decided, I've got a small number of kinds of device that I'm going to configure in basically the same way and feed them a lot of metadata. Finally, differential configuration. Some devices live in a world where all configuration statements start with the running state. Other devices live in a world where you always have to give them the complete configuration. What that requires you do is that you have some amount of logic support to deal with, am I in a bare state or am I modifying the configuration already found? That means that your logic needs to be able to look at your configuration, your proposed configuration, and cut it apart a little bit. It means that you need to be able to recognize if you've got a bunch of non-invertible commands and change strategy from automating a conft process, for example, to actually copying a new config in. Now, generally, this can become really hard really quickly, particularly dealing with things like non-invertible commands. The thing that we've seen, though, is that the actual problem is a lot easier mechanically than the conceptual problem. In fact, this is the biggest idea we found automating device control, is that if you sit down and you look at devices from a math perspective, you say, a lot of stuff I can configure, a lot of different values for those configurations. I could really have a big space of things to deal with. And so you say, I've got to go and figure out how to interpret all of that. That's going to be hard. I'll be back with you in a long time. And so then your operators go out and say, look, I need something that's just going to log in and change the community string once a quarter because I've got 10,000 devices and I have to change the community strings. And I'm doing it once every 18 months when we replace the device, or once every 3 years when we replace the device is not okay. So your operator goes off and writes a little chunk of tickle and comes back. And because he's a good guy, he tells your engineering team, by the way, I've got this little chunk of tickle that changes the community strings. You might want it. And they say, we're trying to get the whole ball of wax, and go away. 6 months later, your guy says, well, I need something to change the password of last resort. And the same interchange happens. What we've been finding on the ground, making automation logic, is that the actual things that people actually do with devices are relatively bounded. They don't ask for them to set up frame relay connections on gig Ethernet, at least not after the first time when they're deciding how that device should be configured, and they remember, it's test lab router 1, not test lab router 2. There's a different card set in there. So your logic doesn't need to deal with every possible setting that might ever be put onto a device. It needs to deal with the way that people actually configure things in your operation, and the policies you're actually setting. And that, happily, is tractable. Just to give you some example of logic that deals with this. This is actually out of our PICS driver, where we connect, we go through a various set of jump hoops to deal with. Maybe you've got a terminal server in the way. Maybe you've got other logic to deal with along the way, like that failover logic. And then we start actually examining, okay, what was the old config file I had? What was the one that was just given to me? And comparing it so that we can push those down in the proper way. Or so that we can decide there's just too much difference here. I have to give up and load a new config. So with that, I'm pretty much done. I'm sure Susan wants you to fill out your surveys. Can I answer any questions? Well, I guess it's late and we're all ready to go home.